So I'll be talking about the way that we use models to predict the future. Predicting the future is obviously something that we're all very interested in. It seems to be a basic human desire. I like this quote by Wayne Gretzky, ice hockey player. A good player plays where the puck is. A great player plays where the puck is going to be. So this captures our sort of eternal desire to know what's coming up, to see what's coming around the corner in order to position ourselves better for it. I was actually thinking about this quote afterwards, and I realized there was an important caveat, which is that this technique only works if not everybody does it at the same time, because at least one person has to play the puck where it actually is, because otherwise the referee would drop the puck and everybody would skate away from it to where they thought it was going to be at some point in the future, right? So this turns out to be important, and I'll come back to it later. Okay, so we all have this enormous desire to look into the future. So for you maybe you're wondering what the job market is going to be like in 2 years' time, once you've graduated, or if you have kids, you'll be wondering what the world economy is going to be looking like in 10 or 20 years' time. But while we want to look into the future, there is this problem which was captured by Yogi Berra. Prediction is very difficult, especially about the future. Yogi Berra, of course, was a baseball player and coach, not an Indian mystic, as I once thought. But I'll give you 3 examples of this. Weather, health, and wealth. These are things which we think we should be able to predict. So I'm not going to talk about all the really difficult stuff, like the way pundits, try to predict what's going to happen in 50 years' time. I'm actually going to talk about relatively what we would consider straightforward predictions. So the first one is about climate change. So the first conference on climate change was held about 30 years ago. And on the first day, one person came up with a model to predict what the effect of doubling carbon dioxide in the atmosphere would be. And he had an answer of a warming of 2 degrees centigrade. The next day, another person presented another model, and it gave an answer of 4 degrees centigrade. And then on the last day, the person who was hosting the conference said, okay, let's add a margin of error to this of half a degree, and we'll call it 1.5 to 4.5 degrees. So this so-called canonical range has remained essentially unchanged ever since, despite the fact that, it's 30 years later, computers have got much better, data has got much better, and there's increasing evidence that climate change is actually happening. I mean, we can measure temperatures getting warmer, and yet we still don't know, we haven't managed to shrink this uncertainty. And in fact, model sensitivity studies suggest that it's actually much larger than that. So this is a bit of a paradox. The most sort of glaring example of our lack of ability to predict the future was the recent financial crisis, which went nearly totally unpredicted by the financial community. Like there was this poll by Bloomberg.com at the beginning of 2008. Not one of the people they polled predicted that a down year, and the average forecast was for a gain of 11%. Instead, stock markets tumbled approximately 40% in that year. So this isn't just Bloomberg. This is institutes like the IMF, the OECD, and so on. This whole thing went unpredicted, despite the number of people who work in that area. Another example is the area which I work in now, biology. 10 years ago, there was a Human Genome Project. So they managed to decode the Book of Life, but it turned out to be a bit of a puzzler because 10 years later, the cost of developing a drug is actually far higher. It costs about $1 billion to develop a new drug these days, and we still can't predict things like the spread of pandemics like swine flu or avian flu. So this is, I really think this is a bit, there's kind of a disconnect here, between, we all want to predict the future. We constantly make predictions about the future, but when we look back and actually see how we're doing, it's not very good. So are these problems related? I think they are. What does this have to do with aesthetics? So what I'll do is I'll go back and give a sort of a history of the Western history of prediction, and then talk about how we actually make predictions, a kind of mathematical models which we create. And then I think maybe you'll be able to see these perhaps as aesthetic objects, and compare them perhaps to the kind of work that you do, I hope. Okay, so In the West, our forecasting history started with this person, the Oracle at Delphi, and so this was the Oracle was a woman who was acting as a channel for the god Apollo, and obviously this institution lasted for about 1,000 years, so it wasn't always the same woman. And the way it worked is that you would kind of queue up, and you could ask her a question about anything that you wanted, about business or war or politics. She would be sitting on this tripod, this three-legged stool called a tripod, and it is said that she inhaled gases from a fissure in the mountain, perhaps ethylene gas, which put her into a kind of a trance. And her predictions were often vague or double-sided. And this is probably one reason, actually, why she did manage to last such a long time, because it was so hard to prove that these predictions were wrong. It worked for Alan Greenspan as well. But she did make one accurate prediction, which was the birth of this guy, Pythagoras. And our history of numerical prediction begins with him. So he was a philosopher, a mathematician, and an Olympic coach, as a matter of fact. And he was considered a demigod by the Greeks. He was named after the Pythia. He was believed to have been fathered by Apollo. And he founded a pseudo-religious cult, which was based on the worship of number. So the key discovery of the Pythagoreans was that musical harmony is governed by simple mathematical laws. So if you take a string and you pluck it and you get a note, and then if you fret the string halfway up and you pluck it, you get a note which is an octave higher. And it turns out that the relationships between notes, the notes that are considered to harmonize together, are related by simple mathematical equations. So this was an astonishing insight at the time, because music was considered the most powerful, mysterious of art forms, and now you've shown that it all comes down to simple numbers. And this reinforced the Pythagoreans' belief that everything in the universe could be explained by simple mathematical laws. This triangular arrangement is called the tetracitus, and this was a sort of sacred symbol for the Pythagoreans, and it has the ratios between the rows actually corresponds to the basic notes of scale. The Pythagorean philosophy was summarized by this list of 10 opposites, which I think is quite interesting in a number of ways. It's a little bit. It has elements of yin yang in it. If you take the left column would be yang, the right column would be yin. It's a little bit left brain versus right brain. The left column again would be right brain left brain because the right hand is controlled by the left brain. But the other really interesting thing about this list is that it says that one is good and one is evil. And the Pythagoreans did sort of try to align themselves with the left-hand column of this. And I think one way this list can be interpreted as a kind of aesthetic key, if you like, okay? Because if you look at some of these ones, such as one versus plurality, there's the idea of unity. If you have a formula or an equation which can explain disparate phenomena in a very simple way, that's considered attractive. Stability, at rest versus in motion. Straight versus crooked, linearity. Light versus darkness. There's this idea of light, which is always being connected with reason. And finally, square versus oblong, which is the idea that something which is symmetrical, and this is really important, and as we'll see in the Greek models, is superior to something which does not have that symmetry. Okay, so if the universe was based on number, one conclusion is that it can be predicted using mathematics. So the Greeks developed this predictive model of the cosmos, and it was used for practical things. It was used for astrology. And they saw the cosmos as this exemplar of fixed order and mathematical logic, what Pythagoras called the harmony of the spheres. And so these models, they assume that there are really two assumptions. One is that everything went around the Earth, so the Earth is at the center. And the other is that everything moves in circles. So this worked okay for things like the stars and the sun, because they seem to go in circles around the Earth. But it didn't really work so well for planets, because if you looked at planets, they would go around and then they would backtrack a bit, and then they would continue going. And so the way they handled that was to add more circles. So the idea is that planets would, go around a smaller circle as they went around a big circle.